Welcome everyone to another lecture video in our data science class. Today we want to talk about linear models. So to get started, let us talk about what we mean when we say we're trying to find a model. So let us go back to our example from our data wrangling chapter, where we were looking at the data set cars that consisted of two variables, speed and distance, and was measuring the distance it took a car to stop when it was driving at a specific speed. And in the black points here are the data points, and the red line that we see here is what we can think of as a model. So when we say we're trying to find a model, what we actually mean is that we try to find a function that describes our variable of interest by some other interesting variable, but still allows for some random fluctuation. So as you can see here, the red line doesn't go through all points, so it still leaves some possibility to randomness for the data, but still the function itself is simply determined by the speed. So in this case here, our f could be, you can think about f as the red line, x in this case is the speed, and y, our variable of interest, is the distance in feet here. And in usual linear model terminology, what we would refer to as speed is it's the predictor, and the distance is the response. So we always try to describe the response via a predictor, and the random fluctuation, so the epsilon here, it's a random quantity, is called residual. So these are usually the quantities, the key quantities we try to look at when we work with models. And here the model then looked like this, like the red function. And when we talk about linear models, we try to restrict our function f to be a linear function with respect to some parameters. So for a simple linear model, we say we have only beta naught and beta 1, which are two coefficients, and these two coefficients form a linear function with respect to the parameters, and they depend on our predictor, so in our case our speed, and we have some random fluctuation. Our residual is epsilon I for each observation from 1 to n, and usually we assume that the residuals are normally distributed with mean 0 and variance sigma squared. So that the mean should be 0 is kind of obvious, because otherwise we would include some error by default into our system. So we try to make our error terms be 0 in mean, but of course we still have some fluctuations, so this is why we still need a variance term. And we say that all of these residuals are independent and identically distributed with respect to all observations. And of course we do not only look at simple linear models, but we could also look at multiple linear models, or sometimes only called linear models, where we use more than these two parameters, beta naught and beta 1, but p plus 1 of them. So we have beta naught all the way through to beta p. And this way we would use not only one predictor, but p of them. And then we still have only one residual term. Okay, how do we find these coefficients? This is basically the goal of trying to find a linear model, is to, well, you have to know what are the predictors. This I assume is a given. But then the point becomes trying to find out what is the value of these two coefficients. And this is usually done by minimizing the residual sum of squares. So yi is our real observation of our response variable. xy is the observation of our predictor variable, and then we try to minimize this difference here, or the squares of it, for all of the observations. So what we try to minimize is this so-called residual sum of squares. And you can visualize this quite easily. So if you click on here, or if I click on here, we would get here, which opens up this this website here where we can look at data sets, I don't know, spending versus salary. And there we could, with this slider here, we could change the parameters, so in our case beta naught and beta 1, and then we could manually try to find those. So in our case, I believe that probably something like this could be the optimal linear model that goes through these points. I can look at the residual, so the residual is always the distance between my straight line that I think is correct and the actual observations. So for each observation I can compute a residual, and if I want to look at how close I got to my best line fit, it's then this. So actually I see that the red line has a lower sum of squared residual compared to my blue line. So if I wanted to, the real parameters are written here, so it's 0.21 for the predictor parameter and minus 1.43 for the constant parameter beta naught. So this is a general idea of how to get it, or how to find these two parameters. But of course, you don't really have to try, I don't know, by trial and error to find these. There are formulas for this. And for the simple linear model, it's quite easy. There are these two maybe complicated looking formulas. At first they might feel weird, but the more you work with them, the more you feel comfortable with them. And here the overlined variables, so xn bar, yn bar, these are the averages. So xn bar is the averages of all observed predictor variables, and yn is the mean of all observed response variables. And then it's a matter of only using these formulas to plug in the data I actually observed to compute or to estimate the parameters. This is why there are these heads here over the parameters. This always denotes an estimation. We can never be sure that what we computed just there is actually the so-called real parameter, but it's always only an estimation. And this is why we denote it by head. And of course, since linear models are really popular, you don't even have to compute that by hand. You can simply call the LM function as for linear model, and then simply tell R what data you want to use. And then same as with the infer package, you describe the relationship between response and predictor via a formula using this tilde. And then what you get is, if you only execute this command, then you will get a result like this, which will restate the function call you did, and then it will give you the coefficients. Here it says intercept. This is always referring to the beta naught, so this constant parameter that doesn't relate to a predictor variable is always called intercept. And here you see the parameter with respect to our predictor speed. Okay, that's basically how you can easily compute or find a linear model for this data set, but this LM function does even more than simply giving this output. If you, for instance, save this into a linear model or into a variable, you just call it linmod and know that you have a linear model in there, then you can actually see, if you, for instance, call linmods, the names of linmod, then you see that there's a lot of information in there. So it's not only that you get the coefficients, but you also get a whole bunch of other information, and all of that combined is what is called a linear model object in R. So LM returns a linear model object. It's just that if we don't save it into anything, into a variable, we actually only see this this result here. But if we save it into a variable, then we can access later on all of whatever it is that R delivers us. It doesn't, not everything has to mean anything to us. Not all of those. I mean, of course, coefficients and residuals, you can kind of assume what is in there, but all the other stuff you don't really need to know. But the point is, if you save it into a variable, it becomes an object that contains a lot of information on your linear model, and that you can use with other functions. For instance, with the predict function by simply sticking the linear model you just saved into a predict function and then giving a new data set. And with this, you can basically predict the speed from the distance it takes to stop with respect to a certain speed via your linear model. Then it's just plugging in speed into your equation and then computing what is the result, and this is what you actually see here. So this is how you use a linear model to predict stuff. Notice here that I've kind of changed the linear model a bit in this slide. I've actually added a +0, which doesn't make any sense in a theoretical mathematical way, because adding 0 doesn't change anything. But in this case, R will understand it as not using an intercept, because in this linear model the intercept will lead to negative distances or possibly negative distances, which doesn't make any sense in our application, because you cannot take a negative distance to stop your car. So this is why I excluded the intercept here, so that everything stays positive. Alright, what else can we get from this linear model? Of course we can use it for prediction, but I also want to maybe have more information. And with summary we can stick a linear model object in there, and we'll get even more information than we had before. So let's go through all of this to figure out what everything means. I mean, the call, it's pretty clear what that means, so we don't need to talk about it. The next is the residuals. So as I said, we get not only we get an estimate of our coefficients, but we also get an estimate of our residuals. Of course, if you predict something, then you can compare it to what you actually observed, take the distance of it, and that is your computed or estimated residual. And if you do that for all observations, then you will get a distribution, and the distribution is basically summarized here. What I want to point out again is that it's an estimation of the residual and not a theoretical residual. So technically what you see here is the distribution of epsilon hat and not of epsilon. It's a subtle difference, but it will make a difference later on, so this is why I'm explaining it, or at least mentioning it right now. Then let's move on to the coefficients. As you can see here, there's no intercept anymore because I've forced to fit a linear model without an intercept. And then we see the estimated parameter for speed. That's pretty clear. The standard error is basically let me explain it that way. If you look at this formula, then you see that this depends on on the y's here, and they are thought of as random. So in theory, you could compute the variance of this whole quantity, and if you do that, then you will get a formula for that. And then if you plug in which will only depend on the x's here, and if you do that, then you can use that formula to plug in your data set you're looking at, and then you will get an estimation of the variance, or if you take the square root, you get an estimation of the standard error. And this is basically what you see here. Then we have a t-value here, so we have a hypothesis test which is included in the linear model. I mean, it's not really part of the linear model, but if we call LM, then also a t-test is run. So basically the t-test statistic is given here for that particular test. And the null hypothesis of that test is that the parameter beta with respect to our variable speed is 0 against the alternative that it's actually not 0. So it's kind of a test of how significant the influence of this speed parameter is. And as you can see here, the corresponding p-value is quite low, so we can think of as this speed variable being significant. A similar thing is the F statistic here. There's also an F test run, so in this case it doesn't change much because we only have one predictors, so only one coefficient, but if we have more predictor, which we'll have soon, then this f-test tests the hypothesis, the null hypothesis, that all coefficients with respect to all predictors are 0 against the alternative that at least one of them is not 0. It's basically a test of are any of the predictors I'm trying to use significant. That's sort of the idea. Then we see this residual standard error. That's only the sample variance of the residuals. And then we see something here which is called the R squared statistic. That part is actually important. That's why I want to focus on it over a bit more detail. This is defined like this. So the R squared statistic is defined as 1 minus the residual sum of squares, which is the sum we've seen earlier, divided by the total sum of squares, which is defined like this. So the total sum of squares is basically n minus 1 times the sample variance with respect to the observations of y. Similarly, the residual sum of squares is the sample variance of, or is n minus 1 times the sample variance of the residuals. So what we see here, if we would add the n minus 1 on both the numerator and denominator, we have the variance of the residuals divided by the variance of the response variable, or what we want to compute. So basically, what this fraction is then is the fraction of the variance that is left unexplained by the linear model. This is the idea. So what is explained by the linear model is, or what is left unexplained, let me phrase it like that, can be seen in the variance of the residuals, and we divide that by the complete variance of the data set, which can be seen in the sample variance of my response variable. And if I divide it by each other, then I get the fraction of the variance that is in the data that is left unexplained by the linear model. It's a bit complicated to explain, but I hope it is clear now. And basically this part here is always between 0 and 1. And the more we are able to explain, or the more variance or variation we are able to explain by our linear model, this will become close to 0. And then similarly, the R squared statistic will get close to 1, and this is what we are trying to achieve. We are always trying to get the R squared statistic as close to 1 as possible. And this is of course not a perfect metric, as all metrics are not perfect, but it's one common metric. And another common metric is one we've also already seen. It's the mean squared of errors, so the mean squared of the residuals, and which would be a different metric, which could lead to say a different result. If you try to maximize or find a model that maximizes your R squared statistic, or try to find a model that maximizes your mean squared error, then you might find different models. This is something you have to be aware of. It's not really a bad thing, but just you have to keep that in mind. And in any case, R squared is really popular. This is why it's always denoted here in the summary. And we usually try to get this as close as 1. So we are already quite close, but still maybe we can improve things. And one thing we need to consider when we want to improve linear models, or our specific fit of a linear model, we will have to look at diagnostic plots. And we can quite easily compute these diagnostic plots either by hand using the data from the linear model object, or using autoplot from ggfortify. And then this way it generates 4 of the most common diagnostic plots, and let's try to look at them one by one. Let's start out with the residuals versus fitted plot. Here you can basically, well, you cannot basically see, you can see the residuals plotted against the fitted values, and you see some of the some points are numbered. These are the rows of the observation in our initial data set, which helps us to identify potentially bad values in our data set to maybe exclude. So for instance, we see here that the residuals are not really completely randomly distributed. If you think about it, our model says that the residuals are IID random normal random variables, and they should all have the same variance. And here you can see, if this is actually true, then you should see a residuals versus fitted plot that has no real pattern in there. And here you can see, as the fitted values become larger, so do the residuals. And also in this area here you don't really have any residuals, but here you have more. So this could be a hint that your residuals are not really IID, or cannot be thought of as IID, and so you might want to take a look at your model more closely. A similar plot is the scale location plot down here, which is basically the same. It just looks at the square root of the standardized residuals. We will talk about what these are in a second, but the point of it is that the residuals here, they use the unit of the data set, or of the response variable. So in this case it should be feet, I think. Yeah, I think it's the distance in feet. So this is given here in feet, and this makes it hard to think of, is this, for instance, this value up here, is that really a large value? And the point of the standardized residuals is that it divides it by some quantity and takes the square root of it, so that it's more comparable to the real scale. And here we see can have again, it should be completely random, and it should look like the blue line should be more of like a straight line. And here we see that the residuals sort of increase as the fitted value increases. As you maybe already guessed, this is not an exact science. At least that's my opinion about these diagnostic plots. You should really look at them if you, at least to make sure that you don't see anything that is really wrong. So it's like hypothesis tests. You can only reject a hypothesis, but you can never prove that your hypothesis is right. The same thing sort of applies with these diagnostic plots. You can never prove that your model is correct, but you can at least certainly prove that your model is wrong if the diagnostic plots look really, really weird. And this is what you see here. So same with hypothesis tests, you need strong evidence to discard your hypothesis. And here in the residuals, things need to be really weird so that you can visually see. At least that's my opinion. I think there are probably some who read a lot of whatever into these plots, but still I think they have some value, so you should at least look at it. Okay. The right hand, the plot here on the top right, it's the normal QQ plot. What this does is it compares the quantiles of the standardized residuals against the quantiles of the standard normal distribution, and it should be on a basically on a straight line if the standardized residuals are actually from a normal distribution, and this is what it tries to show here. This is why there is like a dashed line indicated. This is what it's supposed to look like. But here we see there are some deviations in there, so that might lead us to think that actually our model, together with the fact that the residuals increase, needs some tweaking to get better. And then there is this residuals versus leverage plot, which uses the standardized residuals again and uses something which is called, plots it against something which is called leverage. And the idea of that plot is to find so-called outliers or high leverage points. Let's talk about what either are. We don't really need to understand what's the formula behind the standardized residuals or what the formula is behind the leverage. What we really understand is what they mean. So if a standardized residual is really large, it means that my predicted value deviates a lot from my observed value for a specific observation. And this is, of course, might be a reason for concern. It could be that my model is wrong, or that it's just some outlier. It was like a really high observation for whatever reason. The point is I need to at least be aware that there is something going on there, and this is what the residuals try to detect. So they try to find observations that deviate from my model prediction by a really large amount. So rule of thumbs are that if it's larger than two residuals or 3 residuals, then standardized residuals, of course, then it's an outlier, and then we need to think about what you do with it. Often you just throw out the outliers. And similarly, same as outliers are extraordinary values of an observation, leverage is an extraordinary well, it's also an extraordinary observation, but not with respect to the response variable, but with respect to the predictor. So think about our data set. It only contains values from, I think it's 5 to 25 miles per hour, something like that. Think about if we also had a data point now, additionally to the ones we have, that was measured at 50 miles per hour. Then, of course, it deviates a lot from all the other predictors, that specific observation, and because it's so far out, it might, whatever value it is, it might have a huge influence on how the straight line I'm fitting will look like, because yeah, it's just a huge influential point, and this is what we call a high leverage point. And of course, an outlier can also be a high leverage point and vice versa. And this is why this residuals versus leverage plot tries to find outliers, leverage points, and points that are both. And this is why we look at these two quantities simultaneously. In this case, we would maybe throw out the 49th observation, but I think leverage points are not in this data set. I forgot what the rule of thumbs are for leverage. It's in the lecture notes. You can look at that if you want. Okay, so this is the gist of these diagnostic plots. Let's talk about what are actually the formulas behind the quantities that are in there. So again, our model looks like this. So it's just this linear model here with the normal residual. And what we get is the estimated residual. So it's just the real observed response variable minus the predicted response variable according to our model. And then we can compute two kinds of residuals. We can either compute a studentized residual, which just divides the estimated residual by the sample variance or the sample standard deviation of the residuals. Or what is actually more appropriate is that we divide it not only by this sigma hat, but also by the square root of 1 minus hi, where hi is defined like this. And the reason why this is more appropriate is that if you think about this residual as just a random quantity in the theoretical sense, then you can of course compute the variance of this estimator, and if you do that, then you will see that this exact component here, or this exact term hi, will matter in this variance, and this is why it shows up in the variance, and this is why if you want to standardize your estimator, then you will actually also need to standardize by this quantity. So this 1 minus hi shows up, and the sigma also shows up, and this is why you need both to standardize. And this is why we usually use the standardized residuals instead of the studentized residuals. Okay, and this hi, incidentally, is also how the leverage is defined. Basically, as I already said, it tries to figure out how much one observation of the one observed predictor deviates from all the other predictors. So this is why you divide so this depends on only one I, and you divide it by the sum, which depends on all other predictors. And this way it tries to figure out if this particular observation I deviates a lot from the others. That's the idea of it. Okay. So let's try to figure out what is so bad about these outliers and leverage points. So let's look at our summary again. So this is our base case, and now let's exclude the points that have a standard whose absolute value of the standardized residual is larger than 1. So we include all of these, we filter like that, and then we run the linear model again. And what we can see is that the R squared value increased. And I think it's only one point that we actually got rid of. So only one point helped to increase the R squared statistic by a lot. Well, it's not a lot in this case, but in other cases it can be quite a lot. And similar things can happen for leverage points. So this is why we try to detect them with these diagnostic plots. Okay, so that's a good time to move on to multiple linear models. So this is basically the minimum of what I want to cover with the simple linear model. Let's move on to multiple linear models, but before that, of course, I owe you a dinosaur, so here's that. I'm especially proud of the fact that I also plotted the nose of this dinosaur. So these are two holes where the dinosaur is breathing through. Just for your information, I'm proud of that. And now that you've seen that, we can move on to multiple linear models. And all we have to do to make the transition to multiple linear models is think of our simple linear model equation, which we already know by now, in matrix notation. So we can rewrite our yi is equal to beta naught plus beta 1 times xy plus the epsilon I is for all I between 1 and n. We can think of this as just a simple equation in matrix notation, which looks like this then. And what our estimator then looks like, so the estimator for beta naught and beta 1, or more appropriately beta naught hat and beta 1 hat, this can be computed via this formula. And the nice thing about this formula is that it actually generalizes well for the multivariate case. So if we have more predictors than more than one predictor, then we can use the exact same estimator. So this is the exact same form, but it will simply give us more predictors. And the only difference in this is that the X matrix changes. It doesn't only have 2 columns because it has more than this one predictor, but it has actually P predictors. That's the only thing that changes. I think I forgot to mention that X is called design matrix. This is usually how you refer to it. But the point is it's basically always the observed predictors in the columns, and then you also, for the intercept, you will need a column full of ones. That's the design matrix. And with that and this equation, you can easily estimate the parameter even for multiple predictors. And of course, again, you don't have to do this by hand. You can simply let R do its thing. It's also done via the LM function, and all you need to do is to extend the right-hand side of the tilde here with more predictors. In this case, I wanted to add a quadratic term, so I wanted to add the quadratic of speed, so speed squared. I wanted to make this another predictor, and in order for this to work, I needed to, this is just R syntax, you need to be aware of that, I needed to put this into I and these parentheses here, and then I could simply run the LM command and get a new linear model with quadratic term, and then I can compute summary as before, and here you can see that I got an estimate now for speed and an estimate for the squared speed term. And now you might be thinking, okay, why is there a square in there? Because I thought we were talking about linear models. The point of the linear model is that the parameters are linear. So it's always beta naught plus beta 1 times x times beta 2 plus x2 and so on. The point is you can still have an x2 squared as we have here, but you cannot have an beta 2 squared or whatever in the formula. This would make it a linear, would make it squared within one of the parameters. And this is then not a linear model, but other than that, we're not really restricted to it. You could also think about computing another variable that is just this speed squared and then naming it, I don't know, magic variable, just call it that, and then you could, instead of speed squared, you would have speed plus magic variable in there. And of course, then you wouldn't immediately see that it's a square of something, and that is okay because it doesn't actually matter. The point is the parameter with respect to this new variable, this is linear. And so this is still a linear model. Yeah, this is something you will need to keep in mind. And as you can see here, our R Squared statistic, or this one here, improved. So adding this squared term actually helped. And looking at the autoplots or the diagnostic plots show that the residuals still look a bit better now. All in all of the plots look mostly better now, but again, it's not an exact science. Maybe you, if you were also removing outliers or stuff like that, so here you could see that there's an outlier depending on what you qualify as an outlier. You could also remove this one. Maybe this will change up things even more. The point is that things improved with this quadratic term. Okay, that's how you use multiple linear models. So let's talk about what trouble we can run into with linear models in general. So let's look at categorical predictors. So far we only had numerical predictors, so speed and speed squared. These are of course numerical predictors, but of course we can also have categorical predictors. For example, if you look into the diamonds dataset, which comes with the ggplot2 package, there you can look at this table here, where I only select the variables price, carat. How is that pronounced in English? Is it carat? In any case, it's the weight of the diamond and it drives the price. This is the point of it. So this is like a really influential variable. And the cut is the label for the quality of the diamond. So here we have a quality that is ideal, premium, good, very good, and fair. Out of all of those, fair, I think the ordering is fair, good, very good, premium, ideal. Yeah, I think that's the ordering. In any case, these are, of course, if we want to predict the price now of a diamond, then we will need to take into account its weight. This is what this variable stands for, and its quality. This is what we want to do. And if we look at the data, yeah, you can see that it's not exactly linear, but we could still try to fit a linear model in here because you see like a bit of a parabola shape. But in any case, this is what the data looks like. It's always good to visualize the data so you know what you're talking about. And if we now want to run a linear model, then we'll have to be aware of one thing. If you see here this ORD indicator means that it's not only cut is not only a factor in R, it's also an ordered factor. So it means there is an ordering to it. The ordering I just gave you, it's like fair, good, very good, and so on. That's the ordering. And if you run a linear model with an ordered factor, then it will do something weird. Let's just call it that. It will try to find a square term, the cubic term, and so on, which is not something we usually want to do. And this is why we have to get rid of the ordering, and then we can simply run our LM function. And because the summary statistic or the summary output would be really long here, I used Broom Tidy or Tidy from the Broom package and Glance from the Broom package to get the same information just in tables. We see the result or of the estimated parameters. And what we can see here now is one parameter for the intercept, one for the weight. That's obvious. But now we see 4 estimates for the categorical variable. And this is something which might tip you off, or it might feel weird, because for one it's only 4 variables, even though we know there are 5 categories in this cut variable. And also we don't really know what this cut good looks like, cut very good, and so on. And the solution to that is to know what this means. So I'm telling you, the idea behind this is that we actually transform our cut categorical variable into dummy variables that are either 0 or 1. So 1 meaning it is of that category, and 0 meaning it is not of that category. So it can be either fair, good, very good, premium, or ideal. And of course, if it's 0 on 4 of those, it needs to be 1 on the remaining one. And this is why there are only 4 dummy variables here, because if all of these are 0, then of course I know I have a fair diamond, and this is basically how this works. And of course it can only be 1 for exactly 1 category, and therefore these estimates here can be interpreted as a bonus you will have to put on top of the regular price for a fair diamond, because all of these are 0, so none of those estimates will get added to the price if we have a fair diamond. And then if you get, for instance, a good diamond, then you know the indicator variable for the good dummy variable is 1, and therefore you will add 1,120 to the price. If it's a very good diamond, you will add 1,500 and so on. But and so this is how it works. But if you actually look at what estimates we get, then you see that, well, the premium diamonds seem to cost less on average than the very good diamonds, even though the premium diamonds are supposed to be better or be of higher quality, which feels counterintuitive. And this is something we need to investigate, because obviously our linear model now doesn't agree with common sense. So this is why it's good to look at your estimates closely, and this is why in this case we simply look at the diagnostic plots, and then we see, well, there's a clear pattern here, and therefore obviously I don't have there's something wrong with my assumptions with a linear model, so I need to change something. And when we were looking at the data, we saw that it looks like more a parabola shape and not really like a linear shape. And that was true for all 5 categories of the diamonds quality. And a neat trick is to simply apply transformation to the predictor or to response or to both to maybe achieve something which looks linear. So if we do that in this case, we can see that using log transformation on both the response and the predictors, so both on the weight and the price, then we see that this looks now more linear than, at least more linear than it did before. So we will run a new linear model for this transformed data. For comparison, let us check the R Squared Statistic. It's 0.85. So if we now run the new linear model, so the only thing that changed here is that we have logarithms here now for price and the weight. And then we see that the R Squared Statistic actually increased by a lot. So obviously that helped. Now if we were to predict the price from this linear model, then of course we have to, we can compute or predict a value from this linear model, but then we will get the logarithm of the price. So we need to make sure that we then take this value and put it into the exponential function to get the real price back. This is of course something you need to watch out for when you do this transformation, that you actually retransform it when you want to get to the quantity you're actually interested in. So how did it help now that we transformed the data? As we can see, it did not. There's still something fishy going on here. At least they're more similar now, but still, yeah, the premium is still less than very good, which cannot be right. And yeah, we still need to figure out what is going on there. In the lecture notes, I think I was doing some outlier detection, and then I at least could get into the correct ordering, but still they were not that different. So let's skip right to the most pressing underlying issue there, which is confounding variable. Let's look at the weight and the price, the relationship of the price and the weight. As you can see here on the x-axis we have the price, on the y-axis we have the weight, split into categories and then computed a box plot for each category. You can see that there's like a really strong relationship between the weight and the price of a diamond. If we work to compute the correlation between those two quantities, then we see that the correlation is already really close to 1, which means a really strong correlation. And in itself, this is not a bad thing. This means we have a variable that has good predictive power for the price. But what we also have to be aware of is that it might also distort the picture for other predicting variables. For instance, if we now look at the distribution of the weight for different qualities, then we get a picture like this. So here we look at the density of the weight, and we look at the density for each category. And what we see here is that the ideal premium, so the premium of the best quality, they have really low weight diamonds here. And since it's also correlated quite strongly with the price, it also means that the ideal prices might be lower than if the density was the same for, what was I trying to say? Okay, let me start over again. So the point is the ideal, so the diamonds of the best quality have really low weights, and since weight and price is really correlated that strongly, it will drive down the price of the ideal diamonds. That is not because the ideal diamonds are bad, it's just that they have only really low weight and no one is paying a lot of money for low weight diamonds. That's basically it. So you cannot compare apples and oranges if you were trying to compare ideal and fair diamonds. This is something you have to look out for. And the same thing happens to the very good and the premium diamonds. Look at the density here. It looks really similar, and this is also what explains why the coefficients for these two qualities look really similar. That's more or less it. And this is something known as confounding variables. Here we see the interplay of weight, quality and price, and this is really something tricky and not always obvious to spot, which is why if you see something like that, you need to dive into the data and figure out what is going on. And confounding is the same reason why, as I just said, it could look like the ideal diamonds are you have to pay less for ideal diamonds compared to fair diamonds, which you would see here if you were to run a box plot for both fair diamonds and ideal diamonds. As you can see here, the median price of ideal diamonds is way lower. And this is why here again confounding is doing its thing, and therefore you cannot really compare fair diamonds and ideal diamonds because they are so different in the weight, and the weight is driving the price. That's more or less the story behind this. One last thing we can run into is the issue of collinearity. So we computed the correlation between price and weight earlier, and of course we can compute the correlation between any two numerical predictors. And in the data set you also have measurements of the diamonds in each direction, so X, Y and Z. So length, weight and height of the diamond, length, width and height of the diamond. is encoded in X, Y, and Z. And of course, that is highly correlated with the weight, so with this variable. If it is, if it's a larger diamond, then it will probably also weigh more, and therefore you cannot distinguish these two by a lot. And this is why the correlation between X, Y, and Z and the weight is really strong, and therefore also what the price is really strong. And what collinearity describes is the problems you run into if you try to use two or more highly correlated predictors. So say that you want to use the weight predictor and the X predictor, both to determine the price. Then you can fit two linear models. So the first one, just price and the weight, will give you this model here. What you want to look at is the standard error here, so the uncertainty within this estimated parameter. And now if you add the X variable to that linear model, you would think that things get better because you have more information. But if you do that, then you will see that the standard error for weight at least actually increased. This means that the uncertainty for this parameter increased. And the reason for that is because the weight and X are so similar that the linear model basically cannot differentiate between what influences what, and then things get messy, and this will distort the prediction of the model, or will distort the estimation of the parameter. And to avoid this, you usually try to exclude highly correlated predictors, so only using one of them, and usually that's okay because they carry this similar information, so not much is lost if you throw out all but one of them. That's the idea behind this collinearity. And yeah, this is basically it. That's all I wanted to cover. And yeah, so then see you in the next video. Bye.